Thank you for the warm introduction. Thank you all for coming. I'm Matej, and I'll speak to you about the immortal language, why C++ still matters and why it frankly refuses to die. So I'm Matej. I'm the co-founder and CTO of Omnisearch. I'm an electrical engineer by trade, but I've been programming nearly for 2/3 of my life, so since I was 10 years old. I started in elementary school with programming competitions, and I have, in my professional experience, long experience with writing high-performance, low-level, distributed systems, a lot of things that you need C++ for, basically. And currently, I'm the member of the board for all programming competitions in Croatia, the official competitions at least, so national, international, and everything else. So I'm still very much in the competitive programming scene, and a lot of our employees come from the competitive programming scene. So a bit about Omnisearch. So my friend Marin and I, who was, by the way, my mentor in high school, we founded Omnisearch 3 years ago, nearly. And what's our idea? So we've built a search engine that allows you to find anything in multimedia content. Basically, the biggest thing that we're focusing on now is videos, although we also find stuff in presentations, PDFs, text, and so on. But our most interesting things and demos, as you can see here, are in video. So like we can find what was said in the video, who appeared in the video, what appeared in the video, and slightly more interesting than that, we can find who said what in the video or who appeared with what in the video. So we have a lot of contextual awareness there as well. And when we find something in any piece of multimedia content that we index, we don't only say, as some other search engines do, okay, this is the piece of content, it matches your query, good luck with it. We say exactly, watch this video from this minute to that minute, and that's it. So if you have, for example, we have a lot of customers in the education and the multimedia sectors, so if you have a presentation as mine, but a bit longer, so if it's 3 hours long, 5 hours long, you don't have to watch the entire thing. You can just jump directly into the exact moment where the specific topic you're interested in is covered. So let's talk about a bit about the architecture of the system. So the system has 3 main parts. It has a front end. Of course, users have to interact with it somehow. It has a search engine, and it has a processing layer. So today, we'll mainly focus on the search engine part. But besides that, like, we love Python, and the front end and the processing engine are written in Python. And the first version of the search engine was also written in pure Python. It had satisfactory query performance, and by satisfactory in quotation marks, I mean satisfactory for the end users. So if you type a search query, if you receive results within 2 seconds, that's okay for you. As an end user, you wouldn't say, oh, this is slow, or I don't really like it. I had to wait a long time. But for us, it wasn't that satisfactory. Because, of course, you have to have more infrastructure to serve more users, and so on. There's a lot of technical difficulties if the search queries are slow. It only worked for smaller data sets, so our initial customers had small data sets, smaller than 2,000 indexed entries, although, bear in mind, the indexed entries were videos, and possibly really, really long videos, so like 5+ hours long. So it's not a small number, but it is a small number. So it's not that much of content that was indexed. And the initial search algorithm only supported exact keyword search. So if you search for Python exceptions, we'd only find Python exceptions, like literally. If somebody mentioned Python exception, we wouldn't find that. Although we would find exceptions Python. We were generous there. But it was an exact keyword search. It worked. Besides being written in Python, it would be relatively slow if it was completely written in pure Python, so we did use a couple of speed ups in terms of lookup tables that were pre-calculated, stored in Postgres. But that's it. So like everything was pure Python. But it allowed us to acquire our first 30 paying customers and our first big customers. So it was slower, it supported smaller data sets, but it allowed us a lot of things. So to reach our first major milestones. And again, we love Python, but for the search engine specifically, we had to do something else. So I have a question for all of you to think about. So what is the time complexity of the following two Python snippets? So we have the first snippet here and the second snippet there. So TLDR is basically you want to find out how many L's, letter L's, are there in the string hello, but 10 million times. So hello, 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 hello. How many L's are there? Of course, 20 million. But if we take a look at the first snippet, its time complexity expressed in big O notation is O of n. Because you have to go through all of the characters, check each character if it's an L, increment a counter, and that's it. The second example is a bit more nuanced. Somebody would say that this could be time complexity O of 1, because you only have one operation. But it's not really one operation, because the specific count function that you call also has to go through all of the letters, one by one by one, and check, okay, is this an L, is this an L, is this an L, and so on, and calculate it with a counter somewhere. So basically, both of them are O of n. And now, if we execute them, we get a really, really, really big surprise. So the first example takes nearly 3 seconds to execute. The second example takes 100 milliseconds. So it's 25 times faster. And now, I mean, but they're both O of n. You'd expect them to have somewhat similar performance, but they don't have. The second one is over 25 times faster. Why? The answer is relatively simple. So like example 2 is cheating, because string.count in Python is implemented directly in CPython. So the logic that counts, it's exactly the same as the logic I've written explicitly in Python, but it's written in C. So that, and it's compiled. So that's why it's really, really, really fast. And here we get to the first big reason why C++ is immortal. So big O and calculating big O in Python doesn't really work as expected. So both of the previous examples are big O of n, but the second example was 30 times faster. I mean, we are used to abstract the constant from big O, but a constant of 30 is a really, really significant constant. So like it's an order of magnitude difference, and you can't really calculate big O in Python correctly. So it's the main conclusion is, if you want high performance Python, you have to leverage low level C bindings in Python. And also you can't really determine the time complexity of your solution that you've written in Python a priori. So you have to determine it by benchmarking it later, running it, testing it, and so on. So now we'll transition to C++. We love C++ as well. I have another example for you written in C++ this time. So basically it's the same thing as example 1 was written previously. Although C++ is a bit more verbose, you have to do a bit more heavy lifting manually. So here we have the data initialization loop. So here we build the string of 10 million hellos. And then lower down here, we have the loop that counts. So it goes through all of the characters, checks if any of them is L, increments a counter, and then prints that counter out. It's also time complexity O of n, so it has to go through all of the characters. And if we run this example runs in 55 milliseconds. So it's 50 times faster than the first example, and 2 times faster than the second example. So that's already a pretty nice speed bump compared to Python previously. If we start getting a bit more cheeky in C++ and start using SSE instructions, that are 128-bit wide. This is the loop. So the counting loop becomes a bit bigger. I've removed the data initialization loop because the code wouldn't fit on this slide. But the counting loop becomes a bit more obscure and a bit more complex. You have some loadu, SC128 magic functions. But let's see what happens if we run this example. So this example runs in 31 milliseconds. So it's 90 times faster, 3.5, or nearly 2 times faster even than the previous naive C++ approach. And we can also go further. We can go AVX2, AVX512, although I'll leave that for you as an exercise at home to figure out how faster is it than this example. Hint, it is faster than this example. But let's say that C++ is actually even faster than Python, because these timing numbers that we've seen aren't showing us the entire picture. So like the entire runtime of example 4 was 31 milliseconds. We've seen that on the previous slide. But if we subtract the time that the data initialization loop took, it took 25 milliseconds to run. So actually, the counting loop, so like the nasty and cheeky loop that was really big, took only 6 milliseconds to figure out how many L's are there in the initial string. So if we subtract the data initialization times from all examples, we'll see that example 1 took 2.7 seconds, 60 milliseconds, 30 milliseconds, and 6 milliseconds. So it ends up that C++ is more than 450 times faster than Python for the exact same thing. So if we compare Omnisearch then versus Omnisearch now, our search engine is written in C++ with some helper logic written in Python. It has excellent query performance, so it's faster than 200 milliseconds per query on large data sets. So I'm speaking about data sets that have more than 50 million indexed videos and more than 50,000 hours of video content indexed. And it also has incorporated semantic search like variations, did you mean this, did you mean that? And it uses all of the speedups we could think of. So the snippets that I showed are just a sneak peek. We figured out a bunch more. And now this allowed us to acquire several enterprise customers that are each larger than all of our first 50 customers combined. Without these optimizations, it just wouldn't be possible. So the second step is how we reduced our memory usage by 80%. And I'm comparing C++ to C++. I couldn't compare Python because it wouldn't fit in a 128 gigabyte machine. So we analyzed our memory usage in C++, and we figured out that one specific data structure is using more than 80% of the entire memory that we were using. And we'll call it memory hog this time. And it consists of 4 different elements. So it has a Peter in it. It has first, second, and third. So 3 numbers and a pointer. And we have a vector of memory hogs. So we have a list of a lot of them, of memory hogs. And what can we do with it? There's a lot that we can do with it. But first we have to examine the characteristics of the data itself. So the data, once stored, isn't modified often. Asterisk, it is modified, but it's not modified really often. Read performance in our specific case is much more important than write performance because the index gets updated sometimes, but it gets queried all the time. So read performance is really, really important. The members in each memory hog, so in each list of memory hogs, are sorted by their values. So that's a pretty important hint here. And the values of the members of memory hog are relatively sequential. So if you take a look like 2 memory hogs next to each other, first in the first one, first in the second one, they will be relatively sequential to each other. So they'll be slightly ascending values. So what can we do with the 3 integers? So first, second, and third. Most of them need, so the first requires around 10 bits mostly of information. The second one, 8 bits of information mostly. And the third one requires 24 bits of information mostly. But we do need to keep the possibility of storing larger values because sometimes you do have outliers that are larger than the usual 10, 8, and 24 bits. The answer, of course, always is compression. So we store each integer encoded in memory. The encoding scheme is relatively simple. So we split, you have an example here of an integer, 3802. This is its bitwise representation. And basically what we do, we find which bit is the most significant bit. So this is the most significant bit. All of the other upper zeros aren't really that important. They don't store any information. And then we split the bits into chunks of 7 bits. And then when we encode it, we use each piece of 7 bits into a new byte. We leave the high bit alone. It's reserved. And we basically use the high bit to indicate that it's the end of a stream. So like the number is encoded up to here. This is the last byte of a single number, of a single value. What this means, is that each 8-byte number gets encoded into 1 to 9 bytes. So if it has like all bits, you have to have another byte because we have a 7 to 8 encoding ratio. But we don't really expect really large values. What can we do with the pointer? Ends up that we can do a lot with the pointer. So like Peter, I've written void here to leave out a bit so that it's simpler. But we know that this pointer specifically always points to a structure that's aligned to an 8-byte boundary because it has 8-byte members in it. So what that means is that all addresses that are pointed to in Peter are divisible by 8. So that means that the lower 3 bits are always 0. So that means that we can shift the address by 3 and ignore completely the lower 3 bits. Also, a really nice hint, I'm not sure if you knew this, but virtual addresses on current x86 processors only have 48 meaningful bits. And also the Linux kernel, if you also take a look at home, the source code of the kernel, you can see that the kernel is always guaranteeing you that the high bits in addresses will also be 0. So what do we do? Simple. Shift all pointer values by 3 to the right and use our previous encoding scheme that just encodes only the meaningful bits and throws the leading zeros into the trash. In practice, this reduces pointers from 8 bytes to around 4 bytes, so nearly 50%. Can we do more? Yes, of course we can. So we have a list of memory hogs. Each individual memory hog is encoded into byte streams of varying lengths because like values can be 1 to 9 bytes. You get values that are wishy-washy with their lengths. If we encode them into a vector of bytes instead of a vector of structures, we can pack them tightly. So like we can just write the first value, the second value, the third value, fourth, blah, 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 into a single stream of bytes. That's how you can densely pack the memory hogs, the individual memory hogs together. Can we do even more? Of course. We can always do more. The next thing that we can do, and the previous hint that all of the memory hogs were stored sorted by their values, gives you a hint that you can apply delta encoding to 2 consecutive values that you've stored into the individual byte stream. So for example, the first memory hog has a value of 4th of 3, and then the second has to have 4 because they're sorted ascendingly. It can't have 2. And then you can just store the delta, and the delta was 1. It wasn't 4, it's 1. So that way, even if you have relatively large numbers that are stored in the individual values, the deltas between them fit usually in just 1 byte. So what we end up using is basically around 7 bytes for the first memory hog, and then 4 for most of the other memory hogs, instead of 32 bytes that we used previously. So we're down to 4 from 32. And of course, the results. Like, what did this do in practice? So this is somewhat of a large data set that was indexed in our search engine. It was around 50 million different records, videos, PDFs, a bunch of different stuff. And this is the memory that we used to be able to query it, so 4.5 gigabytes. And it took us 3.3 minutes to build the data structures in memory. So we need to compute like the tree structures and everything else in memory. If we apply all of the previous hints and tweaks that I mentioned, we get the following results. So memory gets lowered to 1 gigabyte, and it stores completely the same information as was stored previously. So we didn't lose any information. That's a 76% reduction. So nearly 80%, I lied a bit, sorry about that. But a couple of other tweaks lowered it even further. So it increased compression even more than this. We're now below 800 megabytes for the same data set. And it also reduced the time needed to build the structure in memory. So the structure in memory can now be built in 2 minutes, 30 seconds. We've also tweaked that a bit from this benchmark. It can now be done in a minute or so. And that's really important because if we use less memory, if we're faster, that means that we can serve the same volume of customers using the same infrastructure. And also, if the queries are really fast, you don't have to use that much compute to serve the same volume of customers, and you can use cheaper compute, or it leaves you more headroom to scale out, your specific deployment of our search engine just by buying bigger metal. So and this scales linearly with CPUs. So like if 4 CPU cores weren't enough to solve all of your querying demands, you just bring up 8 cores. If 8 aren't enough, and there's a lot of cores that you can bring up today, so like you can go up to 768 threads. So there's a lot of headroom that you have if the thing is really, really optimized and really, really condensed. And to get to the second reason why C++ is immortal, if you want to optimize memory usage, so the first reason optimized complexity, time usage. If you want to optimize memory usage, you have to use a language that allows you to tweak the in-memory representation of each object. Because Python, each number, each list, each dictionary, it's a really, really big object. You can take a look at the Python source code. It uses, I think, at least 96 bytes for each object that is stored in the Python interpreter. And that's why if you care about performance, if you care about memory, if you need that, unfortunately, you have to get your hands dirty and you have to use C++ or Rust or C, but preferably one of the first two. And with that, thank you.
Thank you, Matej. Should we give you like a minute for questions?
Sure.
Great, I'll give you the mic.
Hi, great talk, thanks. I have actually 3 questions.
Sure.
Just one.
I will pick first 2 into one.
Okay.
Like how dependent this is on the processor architecture. Like, is it if you switch now to ARM, let's say, do you need to use some other tricks, or all the tricks like virtual addresses characteristics are?
Most of the characteristics are the same. Although currently our engine isn't compilable for ARM because we haven't implemented the specific tricks for ARM, but they can be implemented. So you have, I'm not really sure how the extensions are called for ARM, but you have 128, 256-bit wide SIMD instructions for ARM as well. So we just have to write a couple of, just a couple of helper functions if them for specific ARM. But we haven't deployed anything on ARM yet, so it wasn't that big of a priority, but it's doable.
And would you benefit from like parallel processors like in GPUs?
So specifically for the search engine, I decided that we won't use GPUs. We wouldn't really benefit from them because the query operations require a lot of memory. So you'd be really limited by the amount of GPU VRAM that you can have. Like 80 gigs is the top that you can have, and you'd have to have everything in GPU RAM. Whereas usual RAM, you can go 8 terabytes plus. So you have a lot more headroom there. And also, if you have to deploy the search engine using GPUs, it really raises your cost for deployment. This way, we have really, really low cost for searching, and the latency is really, really good.
And how do you evaluate search results?
That's the black magic of everything, by experience.
Further questions? Okay, I can maybe squeeze in another one. Okay, let me hand you the mic.
My question is primarily like, since you mentioned that you primarily worked on Python before, how complicated it was to like remove all the abstractions that come with Python and convert them to C++?
Very, very complicated. So the conversion from the initial Python code to the C++ engine took, the initial conversion took at least 8 months. So I think the first production version was after a year when it was deployed to customers. And now we've already been building it for 2 years. So the pace does go up as time goes, but the initial burden, you have to have a lot of engineering effort before it starts paying out at all. So like I'd say a year.
Thank you.
Thank you very much. And thank you, Matej. We have to move on, but the lunch break will be soon, so maybe everybody who still has questions can catch up with you during the lunch break. Thank you very much. Maybe